After the Cambrian and Ordovician periods come the Silurian and Devonian periods of the Paleozoic era. The Silurian and Devonian were an exciting time in Laurentia. On the east coast there was a lot of active tectonics going on. On the west coast not so much until the end of the Devonian. Again, mostly a continuation of the passive margin that existed previously. Rocks of this age are included in the Grand Canyon, like here. This is in the upper part of the Grand Canyon called Marble Canyon, and this feature right here is a little channel. It's a cross-section of a channel of the Temple Butte Formation, which is a Devonian estuary that filled with carbonate sediment, a river near the coastline that was subjected to tidal activity. That's an estuary. Life at the time was evolving rapidly. We'll see in terms of fish, we're going to see a lot of changes, and not just animal life, but plant life will start moving on to land. In the water, there's more scary critters like this Eurypterid, which has been around before the Silurian, but is a iconic arthropod of the early Paleozoic. Beginning with the Silurian period, the range was from 444 to 419 million years, and on the ICS time chart, that's right here. This period was another one named after a Celtic tribe from the same part of Western England. Cambrian Wales and the Ordovic tribe and the settlers were all part of this area of Western England. And that's where Silurian rocks were first described. So we have Cambrian rocks in this area, Ordovician rocks, and now Silurian rocks that were first described and studied a few hundred years ago. The geography of the Silurian picks up where the Ordovician left off, with Gondwana dominating the southern hemisphere, roughly situated around the South Pole and extending north towards the equator. You'll have Laurentia separated off to the west, and Baltica and a few other cratonic pieces. But for the most part, all continental landmass on Earth is at or below the equator, with a few minor exceptions. A few other things to note here about Laurentia itself. Here's Laurentia. You can see much of the western parts covered by a shallow ocean, so the craton here is inundated with warm, shallow equatorial seas. Off to the west is the subduction zone, which is creeping ever closer. And in fact, towards the end of the Devonian, it'll start making some noise. But until then, all is quiet on the western front of Laurentia and its shallow marine passive margin. On the east coast of Laurentia, though, a different situation. We ended the Ordovician with the Taconic orogeny, of course, and that island arc collision produced the Taconic highlands. Well, that's going to be followed by another one, and this microcontinental fragment of Avalonia will collide with Laurentia, producing the second Appalachian orogeny. The Iapetus Ocean here still exists in the south. The ocean behind Avalonia is called the Rheic Ocean. The Paleotethys is over here behind Baltica, and notice Baltica is also merging with Laurentia. It's another orogeny to talk about. Panthalassa, of course, is still spanning most of the northern hemisphere. Here's another interpretation of the paleogeography. This is centered on Laurentia, with Baltica and Siberia off to the east, and they are separate from Gondwana, which again is more or less centered on the South Pole. Panthalassa represents the northern superocean, if you will. Huge super ocean to the north, smaller seaways and oceans separating Laurentia from both Gondwana and the other little cratons include Iapetus, which was present in the Cambrian and Ordovician, and the Rheic Ocean. And both of these serve to separate Laurentia from the larger landmass of Gondwana. Well, let's focus in on Laurentia, and you can see that much of it is above sea level during this part of the Silurian, about 430 million years ago. The western side is still a passive margin with a broad continental shelf. This subduction zone with its related island arc still working off to the west, progressively getting closer and closer. You can see Arizona right here, mostly above sea level for much of the Silurian. Here's the active eastern part of Laurentia with the docking of the Taconic island arc and the Taconic orogeny. Here's Baltica over here getting closer, and it is getting ready to merge with Laurentia on the northeastern part. And over here again, another subduction zone bringing closer and closer the microcontinent of Avalonia. As we move forward into the late Silurian, about 420 million years ago, you can see a similar situation. The western island arc has gotten even closer. Still passive margin, just awaiting the collision with that island arc. In the east side, we have the evolution of the Taconic highlands and their progressive erosion and sedimentation of material off under the craton. But now we have the collision between Baltica and Laurentia up to the north, and one that's in the near future. Here's the microcontinent fragment, Avalonia, and that is making its way across the ocean basin there. So this is the Iapetus and then the Rheic Ocean over here. So let's play the little game again with the flip book. Early Silurian, late Silurian. So you can see the island arc on the west getting closer. Arizona pretty much staying above sea level from early to late Silurian. The Taconic highlands maturing and eroding, and the collision of Baltica with Laurentia in the northeast. And finally the closing in of Avalonia with Laurentia on the east side. Let's take a closer look at eastern and central Laurentia. And we have the Taconic highlands. They are eroding and shedding material, in this case off to the west. The line of the highlands extended from Virginia off to the northeast towards New York, and sediments were eroding off the mountains onto coastal plains that were on the margins there of the Taconic highlands, and then eventually towards the shoreline and into the shallow marine areas on the craton. And there were several large depositional basins on the craton that were receiving these sediments from the Appalachian Basin, the Ohio Basin, the Michigan Basin. There was a whole line of major reefs of different kinds. Remember, this is at or near the equator, warm, shallow, equatorial water, so prime reef environment. There were different depositional areas at this time in eastern Laurentia, from shallow marine shelf to reef. There were more transitional environments like tidal flats and beaches, coastal plains, river floodplains and deltas, you name it. In western Laurentia, we still have the transcontinental arch extending down into the Arizona area. You can see here Arizona is the furthest limit of the arch, and it extends back to the east and to the northeast into New Mexico and Colorado. Around the western and southern margins, though, there was a broad continental shelf, so nothing has really changed here since the Ordovician. And this is what the shoreline in Arizona might have looked like, looking off to the west towards the ocean that was Panthalassa. Not a whole lot of life on land, so that picture right there is somewhat indicative of what the Silurian coastline might have looked like in Arizona. Tectonics of the Silurian dominated by continent-continent collisions, at least in the eastern part of Laurentia. Let's look at this diagram here on the left. Here are the two globes of the eastern and western hemispheres on Earth. Laurentia being in the western hemisphere, and this is the eastern hemisphere with Gondwana extending up north of the equator. With Laurentia, the western side still having this island arc, not quite in contact yet, so no tectonic activity or interaction with Laurentia to speak of, but on the eastern side there is a lot of activity. So this lower diagram here shows the middle Silurian. Here is Laurentia. Again, it's labeled as North America here, but that's Laurentia and Baltica, and then Siberia is a little farther north. Red lines are mid-ocean ridge spreading centers. The blue lines are subduction zones. Here's the one off the west coast. The island arc above that subduction zone actually has a name. It's called the Antler Arc here. And there's subduction on the east coast, bringing these continental fragments and larger masses closer and then even into contact with Laurentia. And the orange lines here represent orogenies, so mountain belts, mountain building areas where there's continent-continent collisions. These diagrams over here more or less show the same thing, with Baltica colliding with Laurentia, and that's an orogeny we're going to talk about, and then another one farther south of somewhat lesser extent, because this little fragment of continental crust here colliding with Laurentia is forming another orogeny. And so Laurentia plus Baltica plus Avalonia will all form what is called Euramerica. In this diagram, it's called Laurussia, which is another term that's used, but Euramerica is what we're going to use in this class. Silurian tectonics were very active on the eastern margin of Laurentia. The Caledonian orogeny occurred during much of the Silurian period, and it represents the collision between Baltica and Laurentia. Laurentia being a supercraton and Baltica a fairly large cratonic body itself. When they came into contact, that's a continent-continent collision. And the resulting orogeny, fairly significant. This diagram here is the one we saw before. It shows where Baltica was farther east, separated from Laurentia by the Iapetus Ocean, and that ocean basin would progressively close as this subduction zone brought Baltica closer to Laurentia, where it would finally come into contact with Laurentia and produce a continent-continent collision. Folding, thrust faulting, folds like this exposed in Greenland, that's a result of this Caledonian orogeny. Sea creature, to me it looks like the state of Virginia. I actually grew up in this part of Virginia. Anyway. The Caledonian orogeny helped form the new supercraton Euramerica, which is essentially Laurentia bound together with Baltica, with the Caledonian orogeny, and then those two bound to Avalonia with the Acadian orogeny. Three continental masses together would form what we call Euramerica. In some places it's referred to as Laurussia, but we're going to refer to it as Euramerica. Let's not forget about what's going on in the western part of Laurentia. We have this subduction zone off the coast, and this is a cross-section of what we think the tectonic situation looked like. Here is Laurentia itself, and the oceanic plate tied to it, extending off to the west and subducting down beneath another oceanic plate. This, of course, is the ocean Panthalassa. And so ocean converging boundary, and with the subduction of the one oceanic plate underneath another, you get an island arc. So these island arc volcanoes here situated right above the subduction zone. And so this plate's moving to the right, this plate's moving to the left, and they're getting closer and closer, and this intervening oceanic crust here is slowly being destroyed as it's subducted. And so on the map, here's that intervening ocean basin, here's Laurentia, and then here's the subduction zone with the island arc volcanoes above. This situation back in the Silurian would have modeled what the island arc volcanoes look like today in the Aleutians or Japan, like these. This arc here was known as the Antler Arc, line of island arc volcanoes. Let's turn our attention to rocks of the Silurian, and in eastern Laurentia, which we'll be referring to as Euramerica. The Central Appalachian Basin is a place where there are a lot of sediments deposited and then rocks eventually from those. And in this strat column here, Here's the Silurian rocks, and the early Silurian rocks are mostly cleaner sandstones, and they represent the final erosion of the tectonic mountains. And they're followed by more carbonate rocks, the brick pattern. Some examples would be the Tuscarora Formation in West Virginia. It is a nice, clean quartz sandstone or quartz arenite, and it is extremely resistant, and it forms cliffs and ridges in the Appalachian Mountains. In Virginia, it has a different name called the Massanutten Formation. And it's overlain by younger rocks, which are carbonate rocks deposited in shallow marine settings. And these would be rocks of the Helderberg group. And this is a huge road cut here that you see that's very typical in the Appalachian area. So in the central Laurentia area, the Michigan Basin is one of these depositional basins that we talked about before. And here's where it's located, more or less centered right on the mitten of Michigan. And it's an area of shallow marine deposition just to the west of the land area that was the Taconic Highlands. And these areas are fairly shallow, and there's a lot of reef building from carbonate buildup, and so some of these reefs are extensive barrier reef complexes, and there are also other isolated reefs. Reef means obstacle, and they're obstacle to wave motion and circulation, so the more extensive the reefs are, the more restricted the marine circulation is. And being situated at or near the equator, it's fairly warm. The evaporation rates are fairly high. There's a lot of evaporite deposition. And so the reefs themselves are built up of all sorts of different organisms of the time, which would be sponges and corals and such. But the evaporites would be salts like halite and gypsum and things like that. And so this area is an abundance of Silurian evaporites. The Salina group, just underneath the Muscatatuck group. In fact, underneath southern Michigan, there's huge salt layers that have been mined, and these are some cool pictures of these buried salt deposits which have economic value. And there's a cool website link there that'll take you to a company that describes how they extract the salt, and you'd never know it. It's underneath the Detroit area. Climate of the Silurian was gradually warming after the end of Ordovician Ice Age. So a increase in temperatures from the Ordovician through the Silurian into the Devonian. We can see in this bottom diagram a decrease in the amount of carbon dioxide. It's been progressively getting less and less since the Cambrian. So through the Silurian towards the Devonian, less and less carbon dioxide in the atmosphere, and a commensurate increase in oxygen. Life of the Silurian, I'm going to highlight one of my favorite sea animals. It's a pelagic invertebrate. What could it be? Pelagic's above the sea floor. Invertebrate means it has a shell or exoskeleton. Yeah, you guessed it. It is a eurypterid, a sea scorpion, which inhabited both shallow marine areas and freshwater areas. So there was no escaping sea scorpion, whether it was freshwater or saltwater, and they could tolerate more saline, brackish water environments like these restricted reef areas where all those evaporites are being deposited. There's a cool shale right here with a bunch of different eurypterids preserved. This is a member of phylum Arthropoda, and it's a separate class than the trilobites. The largest eurypterid is on the scale of, I think, 6 or 7 feet. So it's pretty similar to that of the largest trilobite known. I wouldn't want to come across a sea scorpion that large. Imagine if you're walking out into the water on a Silurian beach and something scurries across your feet. Could have been one of these. Well, what could be more exciting than sea scorpions? It would be benthic invertebrates. So shelled critters on the seafloor, brachiopods. And there is a huge diversity of brachiopods during the Silurian. Here are a bunch of different kinds. Orthita is present in the Silurian, Strophomoniida, Pentamerida, Rhynchonolita, spirifers, they're very common. So these are all different types of brachiopods. Well, pelagic vertebrates, can't be talking about sea scorpions because these are vertebrates. They actually have a spine, and we're talking about fish. And the fish from the Ordovician were jawless. Now they're starting to evolve jaw structures. So jawed fish are starting to appear of different kinds. They're still fairly primitive. We call these acanthodians. Okay, and that's just a weird name we give for jawed fish. The jaw itself is evolving from the gill structure. That's how fish got their jaws. And they're starting to become more modern in appearance in terms of not just the jaws, but their paired fins and their scales. Remember the ostracoderms, the jawless fish, were more armored, and these possess less armor and maybe more scales. We finish our chat on the Silurian with land plants. The Ordovician saw spore plants occupying very wet, marshy environments around shorelines and rivers and things like that, and that continues. These vascular plants started to creep onto land during the Silurian, and so we see our first land plants that are vascular, meaning they have a stem and a vascular system to transport the nutrients from the roots to the rest of the plant. There's a cross section of vascular plants showing the network of spaces where the nutrients are being carried. Cooksonia is the oldest known land plant. It's Silurian in age. And so when we look at the evolution of land plants and the number of species present from the Silurian till now, it's a progressive increase with a few deviations. But Silurian is the first real appearance of these, and they will increase in abundance slowly but surely into the Devonian. Ramifications of this: more land plants, less CO2, more oxygen is one effect. The other is plants are a food source for animals, and where the plants go, the animals will follow. And so we're going to see the plants were the first to come onto land, the animals will be next. The Devonian period occurred right after the Silurian, from 419 down to 359 megaannum. And here's the time scale showing where it's positioned: lower, middle, and upper Devonian, with various ages here. Again, we won't concern ourselves with those, but 419 to 359, named for a county in southwestern England called Devonshire. And here's the same map, which showed the Cambrian rocks, the Ordovician rocks, the Silurian rocks, and now Devonshire. So pretty much the first four periods of the Paleozoic were named for areas in southwestern England. And there's some pretty cool places like Valley of Rocks right there on the shoreline. And in this little valley here, there are abundant feral goats. So you never know what you're going to learn when you look up things like this. Geography of the Devonian still includes Gondwana, taking up a lot of space in the southern hemisphere. And there's Euramerica, which is the combination of Laurentia, Baltica, and Avalonia. Gone is the Iapetus Ocean, with the Acadian and Caledonian orogenies closing that ocean basin. But we still have the Rheic Ocean, more of a seaway here that separates Euramerica from Gondwana. Of course, the Panthalassa superocean occupies much of the northern part of the planet. Sea levels themselves during the Devonian are relatively high. There are a lot of areas on these continents that were flooded with very shallow cratonic seas, much like the Cambrian and Ordovician. Let's look at the geography of Euramerica. And here's a paleo map. Euramerica here off on the west side, again, is that island arc, and it is getting very close. In fact, by the end of the Devonian, we'll see it contact the western side of Euramerica. On the eastern side, we have the Caledonian Mountains Baltica merging with what was Laurentia, and down here the Acadian highlands from the collision with Avalonia. Here's the Rheic Ocean seaway, and down here is Gondwana. That's during the early Devonian. This is towards the middle part, about 385 million years ago. Again, here's the equator for reference. Euramerica is straddling the equator. And here's the island arc on the west side. And here's the Acadian highlands and Caledonian highlands, the Rheic Ocean there, and then into the late Devonian, about 360. The Rheic Ocean's getting very tight, more of a seaway, as Euramerica closes in on Gondwana. We finally have contact of this island arc with this part of Euramerica. The southern part down here remains a little less impacted by that collision. So broad areas of a shallow marine deposition. So let's go back to the early Devonian, and you can see how on the west coast things progress. See how sea levels rise and encroach on the continents. We call these cratonic seas. Okay, and so that's a marine transgression as the shoreline moves inland, sea levels rise. On the east coast, see the closing of the Rheic Ocean basin with time. This is all occurring over about 40 million years. Well, let's zoom in on southern Euramerica. And the Acadian highlands existed at this time, and they were the result of the collision of the microcontinent Avalonia with Laurentia to in part form Euramerica. And so it was another form of the tectonic highlands that existed earlier. They might have been a little bit more robust in that the Avalonian terrain was more of a continental mass, didn't want to subduct, so more of a continent-continent collision here, although it was a microcontinent. And so this northeast trending line of mountains we call the Acadian Highlands, or the Acadian Mountains. And just like the Taconic Mountains, they erode and shed debris, in this case off to the west, into these same depositional basins that we were talking about earlier, the Appalachian Basin, the Michigan Basin, and others. So you had a wedge of material called a clastic wedge, representing all these sediments coming off the mountains through rivers and floodplains and deltas onto this coastal plain, and then eventually into these shallow marine basins. Some areas on the craton here were above sea level, and we call these arches. And these arches separate the various depositional basins. In this case, the Cincinnati Arch lies in between the Illinois and Michigan basins and the Appalachian Basin. And we think there were a few narrow passages that connected the various basins. In western Euramerica, during the early Devonian, it was a continuation of the Silurian, the broad continental shelf, and as the oceans rose, we had a marine transgression and the shoreline migrated landward. And so in this marine transgression, we can see a lot of areas of the craton that are now underwater, including much of Arizona. The Devonian was a time of warm, shallow seas in Arizona, much like back in the Cambrian, in fact, a return of the sea. But this would change along the margin of much of western Euramerica by the late Devonian, because we have arrival of this island arc, and here's the block diagram showing Euramerica here and the oceanic crust subducting underneath, giving you this island arc. And this is the narrow ocean basin that was closing until finally this island arc would then be thrown up onto the side of Euramerica. That took place a little bit farther north, and farther south here was still a nice passive continental shelf environment. Collisional tectonics dominate the Devonian as continents continue to converge and add pieces. Euramerica here, the combination of Laurentia and Baltica, would add smaller pieces on the southern margin, the microcontinent Avalonia, and this is the Acadian orogeny. That is the second of the three main Appalachian mountain building events. And everything is closing in. Cratons are coming together again towards another supercontinent. Tectonics of southern Euramerica were dominated by the Acadian orogeny during the middle and late part of the Devonian. And this is the result of the collision of the Abyllonian microcontinent with the southern part of what was then Euramerica. So Baltica and Laurentia collided and now added on the smaller terrain of Abylonia to form Euramerica. This cross-section shows what was Laurentia and how it added on the Taconic terrain here during the Taconic orogeny and the end of the Ordovician, and now during the Devonian it's adding on the Abyllonian terrain. And this is how continents grow. So from Laurentia, now it's added on a few more terrains as Euramerica, and during that process totally closed the Iapetus Ocean. Okay, you can see the ocean now behind Euramerica, between Euramerica and Gondwana, is called the Rheic Ocean. And there's a subduction zone there, and that is going to close over time, bringing Gondwana closer and closer. So the Acadian orogeny is the second of the main mountain building events of the Appalachians. So the first was the Taconic orogeny, where you had an island arc, a subduction zone bringing that island arc closer, finally collision in the Ordovician between Laurentia and that island arc, the Taconic orogeny. Number two was Abylonia, a microcontinent which was brought closer and closer to Laurentia over time by the subduction zone, and it collided, and that formed what we call Euramerica. Then there's another subduction zone over here, and this is Gondwana with what is now Africa, and that subduction zone is bringing that closer and closer to Euramerica, where it's finally going to collide sometime after the Devonian. In western Euramerica, we can finally talk about tectonic activity. It took until the Devonian to do it, though, and at the end of the Devonian and then into the Mississippian was the Antler orogeny. And this was the collision of this island arc we've been speaking of with the western margin of Euramerica. Subduction zone brings this island arc closer and closer. It finally started to contact the cratonic portion here, and it started to load up onto the continental shelf of Euramerica. Lots of folding and thrust faulting, and this island arc terrain, much like the Taconic terrain in the east, was added on to Laurentia. The Antler terrain here was added on to Laurentia on the west side. Lots of thrust faults. The major one is called the Roberts Mountain Thrust. This is exposed in Nevada today. And so this formerly passive continental shelf was deformed by these rocks being thrust up and over onto the edge of the craton there. So deep marine deposits that used to be in this kind of setting here thrust up and over these shallow marine deposits. And so we see that in places in Nevada. This is the first tectonic event on the west coast of Laurentia, now Euramerica. And there's going to be more, but this is the first one. So before the Devonian, it was a nice passive margin. Rocks of the Devonian across southern Euramerica include the Old Red Sandstone, which is deposited during the late Devonian. And here they are exposed in Scotland in the Orkney Islands. There's a sea stack here, very iconic feature. Here's another iconic location where Hutton described unconformities, and this is at Sicker Point, where Dr. Ed Stump from ASU is standing right above the angular unconformity. And these are rocks of the Old Red Sandstone. Above this contact, they're more gently dipped Old Red Sandstone. Also in southern Euramerica, we have units like the Catskill Wedge, which is a group of different rock formations that represent sedimentation off this growing Acadian highlands. This diagram here on the left shows the thicknesses of the different deposits in this Catskill Wedge. The wedge itself is a huge feature made up of a number of rock formations of different types, but the highlands were here, and so the thickest accumulation of sediment is just adjacent here. These are mostly sandstones colored in yellow. Okay, and then as we move farther away, the sediment size decreases. We start to get more mudstones, which are the greener colors. And finally, these sediments are being shed into these shallow marine cratonic basins, like the Appalachian Basin and the Michigan Basin. And that's where the muds start becoming more black shales. And then we start to get a mixture of evaporites and limestones. So that's kind of the map of what the Catskill Wedge rock types look like. In a cross section, again, the Acadian Highlands would be over here on the east side, and the wedge is thickest right next to these mountains, and the sediments are shed to the west, and these rock formations become thinner and thinner as you go that way. So lots of sandstones close to the mountains. As you move away, more shales and limestones. You can notice here coal located in these deposits, because now we have land plants, and these shorelines and coastal plains were very nice environments for these plants to grow. One major aspect of the Catskill Wedge are these shale formations, which were formed in these basins. A lot of these basins were restricted circulation, so there wasn't a whole lot of oxygen in the water, a kind of anoxic environment. So the shales tended to be more dark gray or even black. So these black shales accumulated organic material which didn't decay, and those would end up forming hydrocarbon deposits of coal, oil, natural gas. And so we're going to see this kind of situation into the later part of the Paleozoic in the East Coast with these huge coal swamp basins. But for this time, during the Devonian, there's these large shale formations formed from this deposition, and it includes a number of major shale formations like the Marcellus, Antrim, and others that produce a huge amount of natural gas. In the western part of Euramerica, we have a few Devonian rock formations to speak of, and one is the Temple Butte Formation, and this is late Devonian, much like the Old Red Sandstone. And in the Grand Canyon, it has its best exposures in the eastern Grand Canyon, where it represents river channels like this that are cut into these older Cambrian rocks. These river channels we think were estuaries, rivers flowing across the coastal plain, and an estuary is more or less where the river is affected by tides. And we think that this part of the Temple Butte represents that. And then as you move to the west in the Grand Canyon, you're moving out into the continental shelf, more open marine conditions, and we see the Temple Butte limestone forming continuous sheets, no longer bound by the confines of these channels, can spread out on the continental shelf and form a continuous unit. And that's the Temple Butte Formation. In central Arizona, the Martin Formation is of similar age and deposited in a similar environment, either estuary or shallow marine, but its claim to fame is some early land plant fossils. Here's a picture of Euramerica, and both of these were deposited kind of in this area right along the equator, warm shallow seas. And the cool thing to think of here is both of these units, they represent the transition from a land and river environment to a shallow marine environment. And you can trace it through the Grand Canyon actually, as the Temple Butte transitions from estuary to shallow marine. The climate of the Devonian was very warm. Following this temperature line into the Devonian, it culminates in what's called the Middle Devonian hothouse. Much like the Cambrian and Ordovician warm period, the Devonian was very warm, at least for a portion, and then things would change towards the end of the Devonian. When we look at the carbon dioxide levels, they were dropping at the beginning of the Devonian and then started to rise, and then dropped again drastically towards the end. Oxygen levels were rising and then falling. So this early drop in CO2 with the increase in biomass, basically absorbing CO2, putting out more oxygen, and then for whatever reasons that changed, and so there was less CO2 absorbed and less oxygen produced. But then at the end of the Devonian, we see a massive decrease in the CO2 concentration. So life forms of the Devonian. Let's start with critters that were habitating these large cratonic basins that we've been talking about. On the seafloor, we see lots of coral forming these reefs around the Michigan Basin and others. And these were huge reef complexes of different kinds, whether they were barrier reefs or pinnacle reefs in different configurations. Here's a map of the Michigan Basin. Again, it's centered on present-day Michigan, and a lot of different reef complexes here occupying these warm equatorial seas. A lot of life in these areas. Well, in the Devonian, we have arthropods, and specifically class Insecta of phylum Arthropoda. And so in the early Devonian, just before 400 million years ago, we see fossils of the first insects. And these may or may not have had wings, and these have been uncovered from the Leighty chert in Scotland. Well, talk of Devonian life wouldn't be complete without talking about pelagic vertebrates, namely the fish, because this was the age of fishes. In this geologic age range diagram for fishes and tetrapods, which we'll talk about in a second, this shows the appearance of jawless fish earlier on, and they would continue for a time and then dwindle. They're still around today in a few limited forms, but jawed fish in the Silurian would appear and would flourish during the Devonian. And there are different kinds, from placoderms to cartilaginous fish to bony fish of different kinds. A huge diversification of fish during the Devonian. One type of Devonian fish was called a placoderm, and these were large armored fish, probably the largest animal swimming in the Devonian oceans. And one such placoderm is known as Dunkleosteus. And here it is, the front third of the body probably armored, paired fins and a large tail fin. Dunkleosteus was probably the super predator of the Devonian oceans. We think sharks got their start in the Devonian. This is what we think the early sharks might have looked like, and they're relatively small, maybe less than 2 meters or so, and fairly primitive. But some fairly strange forms evolved over time, including the ironing board shark, or Stethocanthus. Sharks are finally on the scene in the Devonian, and they remain a significant marine life form. These are members of the cartilaginous fish. The skeleton's made not of bone, but of cartilaginous material, and this is what we call class Chondrichthyes. The placoderms we mentioned before were class Placodermi. So we have armored fish in the placoderms. We have cartilaginous fish, like the sharks. Another important type of fish are the ray fin fish, bony fish whose fins radiate from the body, like most modern fish. These are part of class Actinopterygii, however you say that. It's one major type of bony fish. Most modern fish are like this, and they get their start in the Devonian, and they diversify through geologic time. I said it was the age of fishes. Now, we have a fourth major type of fish, and these are called lobefin fish. Subtly different from the rayfin fish in that the fins connect with the body, but at a point, not at multiple points, more or less at a joint or a lobe. So that single difference there is very important. This is a coelacanth, which is a modern lobefin fish. Lobefin fish are not present in great abundances now, whereas rayfin fishes, cartilaginous fish like sharks are. However, these were very important for the evolution of another type of animal we're going to talk about, the tetrapods. Class Sarcopterygii was the lobefin fish. To emphasize the importance of lobefin fish, these were ancestors to all terrestrial vertebrates. We look here, the coelacanth is a lobefin fish, and there's a rayfin fish. The lobefin fish then would radiate into other lobefin fish, Eusthenopteron and Panderichthys, those would evolve into tetrapods, which eventually become amphibians and then reptiles and mammals down the line. Through the Devonian, we see this transition from fish to lobefin fish like Eusthenopteron here or Panderichthys into more advanced forms. These joints here would develop into appendages, eventually arms and legs. We call those tetrapods. So this transition occurred during the Devonian. Well, let's describe what tetrapods are. They include all present-day amphibians, reptiles, birds, and mammals. And back in the Devonian, one of the first tetrapods was this guy here, Acanthostega. Tetra meaning four, pod meaning feet. These limbs or appendages, they grew from these joints from the lobefin fish eventually into this form we call a tetrapod, which eventually would become an amphibian, then reptile, and mammal. So looking at the evolutionary diagram here, from the beginning, our vertebrate ancestors, the jawless fish, would then evolve into jawed fish of different kinds, whether they're cartilaginous or bony. And of the bony fish, there were ray fin fish and lobefin fish. From the lobefin fish, we have tetrapods, which include several different groups, amphibians, and then reptiles, mammals, and birds. The first amphibians would appear in the Devonian, and Ichthyostega is a representative of one of these early amphibians, and it was a tetrapod that had gills and lungs and might have crawled out of the water for a short period of time. Here's a picture of what one might have looked like crawling out onto a log. Lobefin fish in the background here. Here's another picture of the amphibian Ichthyostega. Like any amphibian, they had to return to the water to lay their eggs. And so they were kind of tied to the water. They could come out of the water for a short period of time, but they would return to eventually lay their eggs. These were probably the first true land vertebrates. Even though they didn't totally remain on land, they ventured out onto land, and that was a major evolutionary step. Well, we finished the Devonian talking about land plants. Spore plants still dominated the plant world, although they're becoming more complex. These are typical scenes of a Devonian marshy environment showing lots of different spore plants. Stereotypical ancient earth kind of settings. Look at this geologic age range diagram, and many different spore plants get their start in the Devonian, and there are different kinds from the segmented sphenopsids here to spore ferns and also lycopods, which are more tree-like in origin. Seed ferns, seed plants would come a little bit later though. So in the evolution of plants, again starting from green algae, evolving into vascular plants and land plants, now we're getting into more complex forms. So the plants come onto the land first, and then the animals follow. In fact, why did amphibians come onto land in the first place? Either they could have been following their food source, they could have been escaping predation, probably some combination of the two. One very important type of spore plant are lycopods. And lycopods were really the first large trees to appear on Earth. Archaeopteris is one example of a lycopod tree, and these spread out over a large geographic area, still, since it's a spore plant, limited to wet environments. But one advantage it had is a broader area to collect sunlight, be a little bit more efficient with photosynthesis, and so it allowed it to grow larger. And some of these lycopod trees grew very large, so they're kind of like the sequoia of the Devonian. Very large size made possible due to a more broad leaf structure, more efficient photosynthesis. We know what photosynthesis is. It's taking carbon dioxide out of the atmosphere and putting oxygen into the atmosphere. So the appearance over a wide scale of these trees will have a significant effect on the environment. Well, this is a cool point in the history of the Earth where the evolution of a set of organisms would have a global effect on the planet. and something as simple as trees. The effects of the spread of these lycopod trees across areas of the Earth where no significant land plants had existed before, at least at this magnitude, would have a series of effects which eventually would cascade into an extinction event. So really the primary effect of the increase of this biomass expanding forests are reduced CO2 levels in the atmosphere. More photosynthesis, less CO2. Well, that would have the effect of decreasing the greenhouse effect, which would lead to a cooling effect of the planet and trigger glaciations or ice ages. The ultimate result of the spread of these lycopod forests across the Earth was a mass extinction event. The one that occurred at the end of the Devonian was actually a two-phase mass extinction. This diagram, you can see it here, is a major extinction, one of the big 5 mass extinctions. Changing sea levels due to the cooling that occurred would have affected broad areas of these cratons that were covered with shallow marine areas. As the seas drained off, it would expose large areas, and a lot of benthic creatures and other creatures would have been affected by this. This not only changed these shallow marine areas, but the oceans themselves would have changed. They became cooler and their circulation patterns would have changed, and with decreased circulation, you're not mixing oxygen from the upper parts of the ocean as effectively with the lower parts, and so the deep oceans were probably more anoxic as a result of this, more oxygen poor, and that would have affected life in the oceans to a great extent as well. This diagram here just shows the Phanerozoic and where these cold periods or ice ages occurred. The first one at the end of the Ordovician, the glacial periods that are going to occur at the end of the Paleozoic, the Gondwana glaciations, a fairly cold period of the Mesozoic, and finally the ice age we're living in now in the Cenozoic.